Hi, I'm Morgan Lalouz. I'm here to speak about the thermal performance of a deep open-loop doublet scheme located in a fault corridor with a stochastic approach. This work is a collaboration between GeoResource and Environment, which is a research group, and a private company named Fonroche Geothermy. For those who are not familiar with open-loop well doublet scheme, hot water is produced from a deep aquifer to the surface where geothermal energy is extracted. Then cold water is returned again into the same aquifer at a specified distance, and this will cause eventually the cooling of the heat source. Numerical modeling is here of primary importance in order to make sure that such phenomenon does not compromise the success of the project. This study aims to first limit the uncertainties with respect to subsurface physical properties. For that, Monte-Carlo method is used. Then to forecast the lifetime of the plant in order to ensure the success of the prospective project. And finally, to understand complex transient subsurface processes related to geothermal operation. This study considers a geothermal doublet operating in a collapse through graben. The prospective project is located close to the city of Strasbourg in France in the Rhine Basin. Geological dataset is derived from the European project GEORG, which considers 10 geological entities from Quaternary to Carboniferous. Those strata are crossed by second or third order fault, which mean a thickness between 100 and 1000 meters, and lead to a vertical fault offset of approximately 800 meters. Here, the geothermal target is located at about 4,000 meters deep at the Permian crystalline basement interface. For the sake of simplicity, 4 hydrothermal units were derived from the 10 geological entities that was presented to you. First is Quaternary to Triassic, second in Buchenstein and Permian, the third one is a fault corridor, and the fourth one is a crystalline basement. The study considers a 200-meter width fault corridor in which is located a 300-meter length open hole section that you can see on the close-up view. Numerical modeling of the well doublet is constructed with a FEFLOW model. The 4 hydrothermal units make a cuboid shape of several kilometers of a side. The well doublet located in the center of the model in the fault corridor. Here we consider a geothermal gradient of 45 degrees Celsius per kilometer, as well as a concentration gradient of 58 grams per liter per kilometer. No regional groundwater flow is assumed in the study initially. Now that the mesh is realized, steady-state boundary conditions need to be specified here on the left-hand side in order to achieve steady-state initial conditions on the right-hand side. Hydraulic head is in blue, temperature in red, and concentration in green. All steady-state boundary conditions are first-kind Dirichlet. Geothermal gradient is achieved with fixed temperature of 0 degrees Celsius at the top and 280 degrees Celsius at the bottom of the model. Similarly, concentration gradient is achieved with fixed temperature of 0 grams per liter at the top of the model and 350 grams per liter at the bottom of the model. Concerning hydraulic head, only the surface plane is maintained at 0 meter. So initial hydraulic head is a direct consequence of viscosity and density dependencies on temperature, pressure, and concentration. Now that initial undisturbed conditions are set, transient boundary conditions related to the well doublet need to be added to previous one prior to running the model for 50 years. The well doublet is a model with a fourth-kind boundary condition of 3 positive and negative 350 cubic meter per hour. The injection of cold water is a model with a fixed temperature along the open hole section of the injection wells of 55 degrees Celsius. Here are the results of the reference case scenario after 50 years of productions. On the left is temperature, on the right is hydraulic head. The first line is for time series. Initial temperature at production and injection well is equal to 188 degrees Celsius. Production temperature remained constant for 16 years, which is the thermal breakthrough of the system. Then temperature keep decreasing till the final value of 177 degrees Celsius. Injection temperature is at 65 degrees Celsius as a result of thermal boundary condition. For hydraulic head now, initial hydraulic head is 61 at both injection and production wells. Abstraction and injection of water will cause this figure to decrease from down to 38 meters at the production well up to 105 at the injection well. If we now have a look to the subsurface conditions at 3,800 meters deep for temperature, we can see a clear pathway from the injection well to the production well. This is mainly due to the hydraulic interaction between wells, as well as a relatively high permeability inside of the fault corridor. If we now have a look to hydraulic head subsurface conditions, we can see from broken hydrolines that a contrast in permeability leads to different hydrogeological response of the system. As well, the greater density of hydrolines close to the injection well reveals the high viscosity effect due to low injection temperature. So reference case results were presented to you. The question, some questions arise from this. How can we rely on those figures, and to what extent are they subject to change? To understand that question, we would like to conduct a cross-sensitivity analysis based on Monte-Carlo approach. A brief description now. This is a multi-factor at a time method. Input parameters are hydraulic conductivity and porosity applied to the four entities. 100 random draws constitute our input dataset. Final output data are production temperature, hydraulic head at both injection and production wells, recorded for every year for 50 years of operation. This is the statistical distribution of input parameters. The black solid line is the adjusted law from well test from hydraulic head in the first line, or from core sample measurement for porosity on the second line. The histogram are the initial distribution for parameters. Hydraulic conductivity ranges from 10 to the minus 10 to 10 to the minus 3. The most permeable entity is the number 3, and the least one is the number 1. The porosity ranges from 0.1% to 20.5%. The most porous entity being the number 4, the number 2, and the least one being the number 4. Now, so this is the 100 runs from our batch, and this is temperature result. On the left is time series, and on the right it is production temperature at 50 years of production. We can see from the plot on the left-hand side that we got three main trends. First one is an increasing trend up to 240 degrees. Second one is a decreasing trend down to 150. And the final one is a classical thermal breakthrough like it was presented to you. The main trend is clearly shown by the 80% probability zone, which is delineated by 10 and 90 quantile here on the bottom left. From the histogram, we can tell that final temperature ranges from 140 to 240 degrees. Empirical distribution shows that 80% of final temperature are within the range 160 to 191, with a mean value being about 177 degrees Celsius. In the same way, this is hydraulic head results plotted against time for both production and injection wells, and at final time for production wells only. Injection curves are in solid lines, and production lines are in a dashed line. Minimum and maximum values are obtained from the same scenario and ranges from minus 4,000 meters to positive 5,500 meters at the injection well. This range could seem huge, but when we have a look to the 80 probability zone, it ranges from minus 400 to positive 800 meters for steady state condition. If we now focused on production hydraulic head after 50 years of operation, most of values are within the range 0 to 100 meter. And if we have a look to empirical distribution now, 80% of final hydraulic head values are within the range minus 396 meters to 82 meter, with a mean value about 28. Okay, so we had a look to the distribution of output temperature and hydraulic head at production well, but we now want to cross those results in order to conclude on the probability of the success of the whole project. Success of the project is assumed if final temperature is superior to 160 degrees and final hydraulic head at production well is superior to minus 190. Those statements are reported on the graphics. So for example, 11 scenarios were rejected because they were inferior to the critical value of 160 degrees. In the same way, 21 samples were rejected because they were inferior to the minimum hydraulic head value. So at the end, we can conclude that 68 scenarios were successful. And to conclude as well, we could say that the probability of success of the whole project is about 70%. So to conclude, a synthetic model of an operating well doublet scheme located in a fault corridor was built. Geological uncertainties on geothermal operation based on Monte-Carlo method were delineated, and this resulted in the assessment of the risk of failure under given conditions. Finally, we increased the knowledge on the relative sensitivity of output data related to specific underground conditions. Limits now. Still, the model is geological entities are poor qualified. They are poor characterization of subsurface physical properties. That's why no spatial heterogeneity inside of hydrogeological entities were assumed. So we'd like to acquire a comprehensive georeference dataset. This is a simplified modeling approach of the geothermal system with super hydrogeological entities and simplified fault system. So we'd like to improve the discretization of geological units as well as investigate the role of the fault widths on geothermal operation. Also, this is a slightly underestimated sample, and we'd like to increase stimulated random sample size to 300. And finally, this is a time-consuming process. It's 3.5 hours for each run. That means 13 days of calculation if everything goes right. So we could either buy additional CPUs or start to read your work. Thank you for your attention.